Introduce the last part of the problem solving for chapter 29. I have here a circular loop of wire with radius r equals 0.0250 meters and resistance that is 0.390 ohms. It is in a region of a spatially uniform magnetic field as shown in the figure. The magnetic field is directed into the plane of the figure, which means it is into the page at t equals 0, b equals 0. The magnetic field, this was like, okay, the magnetic field then begins increasing with b as a function of t equals 0.380 Tesla per cubic second times t cube. What is the current in the loop magnetic magnitude and direction at the instant when b is 1.33 Tesla? First, of course, change in flux means changing magnetic field induces a current in the wire. Okay, and E, we know that its magnitude, it equals d phi b over delta t. Now we know that the flux, it is the area times the magnetic field, therefore it is pi r squared times the absolute value of dB over dt. I is EMF over R, and therefore we can say that I, where R is the resistance of the circuit. Then I equals pi r squared dB over dt. We know that b as a function of t is this one. Then when we differentiate, it's going to be 3t squared times the constant. And then also we need to find out what is really the time when the magnetic field is 1.33 Tesla. And from that, we will be able to calculate b as equal to 0.380 Tesla t cube. That equals 1.33 Tesla, and from that the time will be calculated as 1.518 seconds. Then we can plug in this time here, and then we will be able to calculate what is really the the current at this time. Now the next question is, we have here a rectangular a coil that measuring 30 centimeters by 40 centimeters. This is, of course, to calculate the area. Is located inside a region of spatially uniform magnetic field of 1.25 Tesla with the field perpendicular to the plane of the coil as in the figure. The coil is pulled out at a steady rate of, this is the speed or the velocity, 2 centimeters per second, traveling perpendicular to the field lines. The region of the field ends as shown. Find the EMF induced in the coil when it is all inside the field, partially inside the field, all outside the field. Now, when it is all inside the field and there is no rotation, there is nothing to change the current, there is nothing to change the area, then I will say the flux is not going to change, and therefore we're going to have zero EMF. And of course, this is for A. For C also, when it is outside the magnetic field, nothing will happen and we will not have an induced EMF. Now for part B, when it is partially inside, then we're gonna assume that part of it is actually inside the magnetic field, and we're gonna say let's assume that X is the part that is inside the magnetic field. Then the area that is inside the magnetic field is going to be 0.4, which is the width, times X, which is the length. And then I will say the flux is going to be B times A, because like we have like cosine, like we have it is perpendicular to the, which means the angle between the vector A and the magnetic field is gonna be 0 or 180. It depends. All right, therefore, B times 0.4 times X is gonna be the flux. EMF as a magnitude equals D phi B over the dt, and therefore we can say that this is dx over dt, which is the velocity, which is the speed, and that is really the EMF that is induced. The next one, a rectangular circuit is moved at a constant velocity of 3 meters per second into, through, and then out of a uniform 1.25 Tesla magnetic field as shown in the figure. The magnetic field region is considerably wider than 50 centimeter. Find the magnetic and direction clockwise and counterclockwise of the current induced in the circuit as it is going into the magnetic field, totally within the magnetic field but still moving, and moving out of the field. Sketch a graph of the current in this circuit as a function of time, including the preceding 3 cases. Now I will say we have that coil here going into the magnetic field. We are going to, this is about the motional EMF, then I is going to be EMF divided by R. We have BLV divided by R, and that is the length of the conductor here, 0.75, and then we will find that this is the value for the current. The magnetic field through the loop is direction out. The direction is out of the page, and so it is increasing, so the magnetic field of the induced is going to be into the page, because remember these fluxes, if the flux is these fields, if the flux is increasing, they should be opposite to each other. Field of the induced current is into the page and inside the loop, and the induced current is clockwise. Now the flux is not changing when it is, okay, this is part B, sorry, part B, it is when it is, this is not the one, when it is totally within the magnetic field but still moving, we will not have any change in the magnetic field, and therefore EMF and I, they're gonna be 0. And for the next one is gonna be the same as the first one, but we're gonna have the current in the opposite direction. The magnetic field through the loop is directed out of the page and inside the loop, and the induced current is counterclockwise. The last part, we are going to graph it, then we're going to assume the clockwise currents to be positive, and then it's going to be 0, and then it's going to reverse the direction, and therefore this is what we are going to expect for the graph of the current versus time. Here it's a problem about a solenoid. A long thin solenoid has 900 turns per meter and radius 2.5 centimeter. The current in the solenoid is increasing at a uniform rate of 36 amperes per second. What is the magnitude of the induced electric field at a point near the center of the solenoid? And I would say 0.5 centimeter from the axis of the solenoid, 1 centimeter from the axis of the solenoid. I listed my values here, and we know that R dot E dot DL equals negative D phi B over delta T. In order to calculate the induced electric field E at a distance R from the center of the solenoid, we are going to say first B equals mu 0 Ni for the solenoid, and then we will be able to integrate the path that for the surface here that we're gonna have, which is for R, where R is less than delta R, less than the radius of the circuit. Now here I will say this is the left hand side, this one, and this one is the right hand side. I need to calculate the left hand side. This is the one, because it's gonna be E, and dl is gonna be 2 pi r. Then here I will say also for the right hand side, we can calculate that as pi r squared dB over dt. And because we know that these two are really equal, then we can put the equations together, and from that we can conclude that E should be 1/2 R dB over dt. Now the B is mu 0 Ni, then dB over dt is going to be mu 0 times N di over dt, and from that we will be able to calculate what is really the electric field. Okay, we can repeat that calculation for part B, where R is 0.01 centimeter, and we are still inside the solenoid, so the expression applies, and then we will be able to calculate that as E equals 2.04 10 to the negative 4 volts per meter. I think this is the last one. In the circuit shown in the figure, the capacitor has capacitance C equals 20 milli. I think this one is micro. Yes. This one here should be micro. Here I'm gonna write this note micro. Farad. Okay, then here this should be microfarad. Okay, and is initially charged to 100 volts with the polarity shown. The resistor R0 has resistance 10 ohms. At time t equals 0, the switch S is closed and the small circuit is not connected in any way to the large one. The wire of the small circuit has a resistance of 1 ohm per meter and contains 25 loops. The large circuit is a rectangular 4 meters, while the small one has a radius, has a dimension of, while the small one has 2 meters by dimension A 10 centimeter and B 20 centimeters. The distance C is 5 centimeter. And of course this figure is not drawn to scale. Both circuits are held stationary. Assume that only the wire nearest the small circuit produces an appreciable magnetic field through it. First, A, find the current in the large circuit 200 milliseconds after S is closed, and find the current in the small circuit 200 milliseconds after S is closed, and find the direction of the current in the small circuit. justify. Okay, first like after we close the the switch, the capacitor is gonna start the process of discharging, and therefore I is going to be the maximum current times E minus T over RC. We need to calculate RC, and that RC is gonna be 200 microseconds. And then we can say this is the voltage 10 over 10, 100 over 10. And from that, we are going to have the equation, and we will be able to calculate the current as 3.7. We know also that the current is going to decrease, and then the flux decreasing, then the B original out of the page, and we should have the B induced out of the page as well. Then the current is going to be counter clockwise. Also, we are going to use the result from exercise 29.7, where theta, the flux is going to be C from C to CA mu 0 IB over 2 pi R dr. And we can evaluate the integration, and then we can calculate EMF as negative n. This is the number of turns, the flux, the rate of change in the flux, and then from that we will be able to calculate the EMF, and then divide by R. Then we are going to have the 1.33 milliamperes. Of course, the magnetic field is gonna create a counterclockwise current as explained above. We can actually make the estimate, we can make the approximation that only that wire is gonna cause the the induced current, because the other wires are really far compared to the dimensions of the circuit. Thank you, and have a great